Let me just share my screen here. Okay, hopefully you can all see the slides. So thank you, Michael and Malik, first of all, for organizing this great summer school. Thank you, Luca, for inviting me to be part of this talk. So, sorry, just moving a window out of the way. So today we're going to be talking about, Luca and I are going to be talking about planning and plan execution for human-robot interaction tasks. And as Michael said, we've both done some work in this area for some time. In particular, today we're going to take a look by motivating a lot of the work we do by considering what we mean by things like public space robots and human-robot interaction. We're then going to look a little bit at social robots and talk about some of the planning techniques that we think are useful for this task, and also the types of planning that we employ ourselves. So we're going to give you a few examples of two planning systems that you may or may not be familiar with, but we've been working on for some time now. And then in the second half, we're going to talk a little bit about plan execution and basically the idea that there's a lot of uncertainty in HRI. It's a very complex problem space, but it also offers a lot of opportunities for deploying the kinds of planning that you've learned about this week in real applications that can really make a difference in real world environments. So I want to start just by showing you a little video here of a public space robot. So this is a video from 2016, the Maker Faire in Rome. This is the robot Alfred. And don't worry so much about the robot, but look at the environment. So we have lots of people milling around, people now kind of swarming the robot. We've got a noisy environment, lots of background chatter. We've got people walking up. We have, people pointing, people touching. This is the environment in which we're working here. So it's a very complex environment. It's very noisy. It's a very uncertain type of space. So if we look at examples here, here's a range of public space robots, some of which you may have seen. Probably a lot of you have seen the Pepper robot. Seems to be amongst the more popular ones these days. But various places, often in malls, you see different types of robot embodiments that are meant to exist in these worlds in which we live in. So take a robot, put it into this kind of public space, and deal with the problems that arise about what's going on. Aside from the environment, we also can consider the types of tasks we have to perform here. So for instance, let's take this robot we just looked at, the bartender robot, and consider the types of interactions you might have if you go into a pub or a cafe, something like that. So you might have people approaching the bartender or waiter, something like that. And if the robot is taking the role of the bartender, it needs to respond. So we might have an interaction, something like this. So two people come in, they walk up, the robot says, "How can I help you?" Person places an order, then maybe somebody else walks up at that moment, tries to attract the attention of the robot. The robot has to deal with the situation. So the robot might say to that person, "Well, hang on, just a moment," serve the first person, ask the second person what they'll have. Person might order, serve that person, thank the other person for waiting, and then serve them their drink. So again, you see there's a lot of complexity here, even in something that might be a simple task-based type of scenario. Someone comes up and is trying to order a drink. So in all of these kinds of scenarios, we're faced with the question, well, what should the robot do next? So we have this environment, we have this, potentially quite complicated, quite noisy, uncertain environment. And what you'd like out of that is you'd like some rational set of behaviors that hopefully governs what it is you're trying to achieve. So you can imagine in this kind of scenario here, we might come up with a strategy that looks like this. I greet the customer, I ask the customer for their drink order, I acknowledge that I understood what it is they've ordered, I go off and pick up the correct drink, bring it back, and I serve it to the customer, and then maybe I thank the customer, I take their money, whatever it is. Now, if you think about it in this context, it sounds like planning would be a good tool for this, because we have a type of plan generation problem here, right? We have concrete actions that we need to perform. We have a goal we're trying to achieve. So in this case, we're trying to meet the needs of the customer, ensure that all the customers that come into the restaurant or the bar have been served. So it looks like planning would be good for this kind of task. Now, during the course of this week, you've probably heard about lots of different types of planning, and of course, classical planning is certainly one of the more popular choices. Now, if we think about classical planning, we realize very quickly that there are some difficulties with this. So first of all, the agent's knowledge about the problem is complete. So the agent would have to have, the planner would have to have full and perfect observations, for instance, of the world, full knowledge about how its actions will evolve in the world, how they'll change the world. We would have to model the actions with deterministic effects. And typically in classical planning, we have a model of instantaneous action. So the execution time doesn't matter. So in terms of what this means, given some representation of the world state, the agent state is going to be exactly the same. What it believes or what it knows or what it thinks is true about the world is going to be exactly the same as the world state. We have this complete, perfect observation, deterministic types of effects. Now, unfortunately, hopefully you've seen from the videos and what I've been saying with this example scenario, this kind of human robot interaction scenario is much more complex. And so this raises a lot of challenges for planning. In particular, for instance, just to start with, the planner's knowledge of the problem is probably going to be incomplete. We have humans involved in the scenario. Humans are inherently unpredictable, especially when they're interacting with other humans, or in our case, with robots. So we don't know when a human comes in and walks up to the robot what they're going to say, what it is they want to be done. And even in the case of the bar scenario here, we don't know what drink it is they're going to order. Or maybe they're just going to ask us for a menu, or maybe they're going to ask us for directions. It could be completely unpredictable, even in these quite constrained, quite task-based scenarios. The next thing is that the observations are going to be noisy. So again, you saw from the first video, we had lots of background noise. We had lots of people milling around. So even if you have really good sensors, are those sensors picking up information about the person that's interacting with you? Or are they picking up a conversation that's behind the robot or across the room? So even in the best case scenarios, assume that your observations will be noisy. Action effects are non-deterministic. I might plan a certain action, but then if I perform that action in the world, it may not actually turn out that way. This is especially true if I'm planning actions to do with language. I may, for instance, ask a question of a human and they give me a completely unpredictable answer. Actions also have duration. They take time. They aren't instantaneous when we're dealing with these things in the real world. And actions can fail, especially on robot systems. It's often the case, even with the best engineered systems, that we see failures both at the physical side and also things to do with communication. We also have this problem of humans. If you're going to do human-robot interaction, you've got to deal with the human component. Humans aren't obstacles towards reaching your goal. You've got to deal with them. You have to either model them or at least have an understanding of what it is humans are going to be doing in this kind of task. So a lot of the work that Luca and I both do, and other people in the field, certainly within the planning community, there's a number of people, and I'll highlight some of those later on. We're interested in what we would call cognitive social robots. So we're interested in equipping these kinds of physical systems with high-level reasoning capabilities. And these are things of the kind you've probably heard about this week. So we want them to be able to reason about goals. We want them to be able to reason about actions, about plans. But we're also interested in things like perception and collaboration and how they fit in with the rest of the world. We also, in the approach we tend to take, have an explicit representation of knowledge. So these are systems that have some knowledge about themselves, about the environment in which they're operating in, and most importantly, the other agents. So the fact that they exist in a multi-agent world. The extra challenge here, the extra twist, if you will, is that we also care about the way in which the goal is achieved. So often we need to do this in the context of social norms. There are particular ways we're expected to act because this is the way that, for instance, people act in society. And so there's a focus on things like acceptability. Now, the extra challenge here is also just the public perception of these things. So if you ask people about what they think robots should look like or how they should act, often you get this Star Wars view. You know, they should be C-3PO. But then to us, we have this very engineering or scientific kind of view about trying to understand, trying to model, trying to come up with the tools that let us do this task. So even if we look back at this task-based interaction that I started with to motivate things, you can very quickly see that even the nature of action here is quite complex. So for instance, the robot saying, "How can I help you?" You could think of this as a type of information gathering action, right? You're trying to kind of sense, if you will, what it is the person is here for. Why have they come to interact? Later on in the interaction, you see things like the robot saying, "Well, just a moment, please." You can think of this as a social action. This is responding to the fact that, we need to give humans some cues as to what we're doing at certain times. The robot actually handing over a drink. You can think of this as a physical action, right? So this is something maybe we're pretty good at in planning. I pick up an object and I hand it over. And you can see we have even in this very simple interaction, we have a set of these kinds of actions throughout. So it's a complex problem, but luckily we do have tools for dealing with this. One of the interesting observations about this kind of problem is this idea that the agent's representation of the world is potentially different from the actual world state. So as we saw in some of these examples, we don't know why a human is interacting with us, or we might have made certain assumptions about why the human has interacted with us. But it's possible that we got it wrong. So for instance, if the world looks like this, this is just a simple little blocks world example. Maybe we believe the world actually looks like this, and so there's a slightly different configuration here. In terms of HRI, it could be that you said to the bartender, I'd like a Coke, and the bartender somehow heard that and thought you said a beer. So there's always going to be noise. There's going to be errors, but we can try to deal with this kind of distinction between the world state and the agent state. We might also have uncertainty about the different views of the world state. So it might be the case that in fact we consider as being possible a couple different options for the world state. So we might be certain about some parts of it, but then we might be, not so sure about other parts. So it could be the case that, these blocks are stacked A above C, or maybe it's the case that it truly is C above A. So inherent uncertainty in the problem. Now, one of the tools that we can use for reasoning about these kinds of problems, dealing with this type of knowledge and these problems of noise and uncertainty, is epistemic modal logic. And these are simply logical frameworks that allow us to represent and reason about knowledge and belief. Now, if you've done any work with ordinary logic or normal representations of the kind we tend to use in classical planning, you can think of epistemic modal logic as just adding an extra operator. You put a K in front of your formulas. And the idea here is that this is now representing a knowledge formula. So KA is saying, I know that A is true. So I'm definitely certain that A is true. In other words, A equals false is an impossibility. And then we can also talk about things like, knowing that A is false. In other words, A being true is an impossibility. And we can have the negation of these kinds of things. So this one would say, in the bottom left, would say, I don't know that A is true. So that admits the fact that A equals false is still possible. And I could also say that I don't know that A is false, admitting the fact that A equals true is still a possibility. So we have a simple way with these modal logics of capturing some of these inherent ideas about knowledge. Slightly more interesting ones, if we start combining these ones, we could say things like Ka or K naught A to represent the idea that I know the value of A. So this is different from saying I have no information at all about A, but I'm not sure if it's A or if it's not A, but I have knowledge of this. Like we could also say things like I don't know the value of A, so I not know A and not know not A. Why this is useful is we can then put these things together to start thinking about model sensing actions or information gathering actions. So for instance, a simple type of sensing action to gather information about coming to know A might be something like this. So as a precondition, I say, I don't know the value of A. And as an effect, I come to know the value of A. So in other words, again, you could think of this as a type of action that's modeling something that will allow you to acquire information from the environment. Possibly this is a sensor that's on your robot. Possibly this is asking somebody a question and expecting a response. So this epistemic state representation is potentially quite powerful. So not only can we represent this idea of, knowledge about the world or not knowing something about the world, we can use it to represent the knowledge and beliefs of other agents as well. So I could talk about the fact that, there's a world state. Some agent has knowledge of that world state, which may be incorrect. And then another agent has knowledge of that other agent and what they believe, which might also be incorrect with respect to the original beliefs of the agent or with respect to the individual beliefs of the world. So in other words, we really have quite a powerful mechanism here. One of the important things is whether or not we need to deal with these kinds of explicit representations of human models. And most of the time, we do need some representation of it. So there's some great work I just wanted to point out here by Chakraborty that has looked at actually trying to capture these kinds of models, the mental models of humans from the planning perspective, to be able to then plan with respect to what you believe to be the model of the human to try to improve your ability to plan. And of course, we can do this with these multi-agent epistemic logics as well. If we have, for instance, two agents, we have the human and the robot, we could write formulas that say, H knows A, or H knows not A. In other words, H knows the value of A, but R does not know the value of A. So again, we can make these assertions with respect to the particular agents, and we can nest this kind of knowledge. So we could say more complex things like H does not know that R knows the value of A. And then you can get deeper and deeper and deeper into the reasoning. So if you're interested in this kind of formal reasoning, there's been a lot of work that's been done over the years in various frameworks, logical frameworks for representing these types of problems. Now, it is a challenging problem, even though we have these kinds of tools. So thinking about something like how would you model an ask action might be a difficult task. So what does it mean to, in terms of knowledge, to ask somebody for a piece of information? So we might have a model that looks something like this. So if the robot knows that H knows the value of A, and the robot does not know the value of A, then it can ask H for A, and as an effect, H knows that R does not know the value of A. So in other words, by asking someone, you're hopefully conveying a piece of information about the fact that you believe something and you believe that they believe something, and will hopefully supply the answer to you. So there's a lot of complexity that that can be involved even in this. This is a relatively simple type of reasoning problem here. How would you go about asking another agent for a piece of information? So epistemic planning then is trying to plan at this level of knowledge, trying to deal with all of these kinds of mechanisms to do with the fact that you might have beliefs about certain parts of the environment, you might have no beliefs about other parts, your beliefs might be incorrect, they might be uncertain, you might have beliefs of other agents. Now, there are some really nice planning frameworks that are being developed for this right now. Dynamic epistemic logic is a very general framework. It has a lot of high complexity, but it lets you represent some very complicated planning approaches. So we're seeing a lot of tools starting to come out that use this Dell approach. And I've pointed out a few people here that are worth looking up if you're interested. So for instance, Thomas Bolander at DTU, Bernhard Nabel's group at Freiburg. Hector Geffner is also doing a little bit of work on using classical planning approaches to do epistemic planning. And also just a plug for some tutorials. There was a tutorial at KR on epistemic planning this year, and there's an upcoming tutorial at ICAPS on epistemic planning. So if you are interested in this idea, especially from the Dell side, I'd invite you to join one of these sessions. Today, though, for the rest of the section, we're going to consider two other approaches to dealing with epistemic planning. I'm going to talk for a little bit about a system I've worked on called PKS, and then I'm going to pass off to Luca, who's going to talk about some specific epistemic logics that he's used for planning in a system called ALCK-NF. So PKS stands for planning with knowledge and sensing. This is an approach that actually goes back to my PhD days, and so it has kind of beginnings going back quite a while. But it's an approach that we've extended. We continue to use. We use for real applications. We're currently working on some industrial applications of this. It's an approach to contingent planning, and we in particular are interested in modeling incomplete information and sensing. The important thing in PKS is it gives you a knowledge level representation of action. So actions are modeled in terms of the changes they make to the planner's knowledge state. So these kinds of ideas we've been talking about with modal logic, rather than the world state. So this is not like the way you would model the problem in classical planning. The approach we take with PKS is it's based on manipulating a collection of databases. Each of these databases represents a particular type of knowledge the planner can have, and there are tight syntactic restrictions. So this restricts the form of the knowledge that we can represent, but hopefully in a way that allows us to generate plans quite easily and quite simply. So this is what knowledge representation looks like in PKS. These funny K references on the left here are the names of the knowledge bases we have. So we have something called KF, which is used to represent knowledge of positive and negative facts about the world. So you can think of this as being very similar to a strip style representation, except we don't have a closed world assumption like we would have in the classical planning problem. So we could represent things like block A is on the table. We know the gripper is not empty. We know that some customer seeks attention. So simple assertions of properties of the world. The more powerful features of the knowledge representation have to do with representing this idea of knowing whether something is true or knowing the value of certain types of information. And this really lets us represent the kinds of information that would be returned by different types of sensors. So you could imagine a binary sensor that's able to tell you, is an object heavy or not? Has a customer ordered or not? We're able to represent that information here using this particular database called KW. KV allows us to represent multi-valued sensor information. So these are things like sensing what the actual weight of an object is, or asking a customer for their drink order. So some sort of property of the world that might map to a numeric value, for instance. We have some way of representing that piece of knowledge. And then we also consider other types of knowledge, something called exclusive or knowledge. This is the idea that we might know that one of a set of possibilities is true, but we don't know which one. And then an idea called local closed world information, which goes back actually quite a number of years. This is the idea that certain parts of your problem, you might in fact have complete information. So for instance, say I have something like a box, I open up the box, I take a look inside, and I come to know all of the objects that are in that box. Now, I don't know all the objects in the world, but about that little constrained part of the world, I might have complete information. So this is the representation. This is all the types of knowledge that we can deal with. On the reasoning side, we can ask very simple questions about the knowledge. So we can ask, does the planner know that something is true, or know that something is false? Or does it know the value of something? Does it know whether something is true? So all these types of knowledge we've been motivating with the modal logic. We have very simple ways of actually asking questions about that. So then from that observation, we can build actions. So on the left here is a what I would call a world level action. This might be the way that you write an action in classical planning in a, it's not PDDL, but in a PDDL type of notation. So how you might do a blocks world grasp action, right? Provided the gripper is empty and the object's on the table, I can grasp the object, and as a result, the gripper isn't empty, the object isn't on the table, and the object's in the gripper. In PKS, we raise the problem up to the knowledge level. So now all of the assertions we make about things like preconditions and effects have to do with knowledge. So in this case, we're saying we can grasp an object if we know the gripper is empty and we know the object is on the table. And as a result, we know the gripper isn't empty, we know the object isn't on the table, and we know the object's in the gripper. So we've raised the level of reasoning up to this knowledge level. Where this is really powerful is when it comes to doing things like representing sensing actions. So for instance, this action description on the left here could capture the fact that I could sense that I could sense whether or not an object is empty if I know that object is on the table. And as a result, I come to know whether the object is empty. So you could think of this as modeling a type of visual sensor, right? I take a look at the object and I come to know, is that object empty or not? So we can capture that using this type of epistemic representation. Similarly, this action on the right here, would capture an idea. I could sense the weight of an object. If I know the object is in the gripper, as an effect, I'll come to know whether or not the object is heavy, and I'll come to know the value of the weight. In other words, I'll come to know a numeric value. So again, we have a type of a simple type of sensing action here based on picking up an object and actually determining whether or not that object is heavy, and making maybe an estimate of its weight. Okay, so how does PKS then do actual planning over this? It's simply a transition system and a search through now the knowledge states. So rather than just reasoning about the world level state changes, we instead are reasoning about how these different types of knowledge are evolving when you apply the actions. So if we look at the actions here again, you can see that the effects are modeled with certain adds or deletes to particular knowledge bases. So in other words, we've specified the update. We've specified how the knowledge changes as a result. And now at the planning level, we can just simply search through that. So for instance, if we had a knowledge base that just had factual information, I know the gripper is empty, I know the bottle is on the table. After applying this sensing action, we would end up in a state where we have, again, still factual information, but now we have no weather information as well. So after sensing whether or not the bottle is empty, I come to know whether the bottle is empty. And then we can apply other actions. And we just make these kinds of updates to the state. Now, there are two interesting observations here, and I don't have time, of course, to explain the system in its entirety. But if I have no weather information, so if I know whether the bottle is empty, this means I'm in a state where it's possible that the bottle is in fact empty, or in fact that it might be not empty. So I can form a conditional or contingent plan here. I can break the plan into branches, and I can start planning about each of these possibilities. So I can turn my KW knowledge, my no weather knowledge, into definite knowledge, and use that to try to build different contingent branches into the plan. The second observation is if you have KV, so if I know the value of something, so for instance, this is telling me I know the value of the weight of the bottle after I sense it, I can use this as a type of runtime variable. In other words, I can use this as a placeholder in my plan. So I don't know what the numerical outcome of this is. I might know that at execution time. But from the planning perspective, I can use this as being representative of whatever that value actually is. So these are powerful mechanisms, and I mean, my planner isn't the only planner to support these, but these are powerful mechanisms that you get by reasoning at the epistemic level, being able to make these knowledge level assertions. Okay, so how do we use this for HRI? Well, we use it for modeling the different types of interaction actions that we have. So these are some actions that we used in the bartender domain. And you can see that some of them are pretty straightforward here. They're not that complicated. So for instance, to greet an agent, I can say, well, if I know I'm not transacting with the agent and I know they haven't ordered, then I'll start transacting with the agent. So nothing very complicated there. The ask drink action is potentially the more interesting one. So I can ask an agent for a drink if I know I'm transacting with them and I know they haven't ordered. And as a result, I come to know they have ordered and I know the value of the drink they've requested. So again, we have this knowledge level assertion that we're making here. Similarly, we have actions for serving the drink and saying goodbye. So I can serve a drink if I know the person has ordered, and if we know the value of the drink they've requested, and we know that request is the same as the drink that we're trying to serve them. So again, we have this knowledge level assertion using this idea of knowing the value of the drink. So when we plan over it, then we can generate plans that look like this. So I can greet the agent, I can ask them for their drink, I can acknowledge their drink, and I can serve them the drink they requested. So two things here. First of all, this is very similar to the type of plan that we motivated at the beginning of the talk with what the agent should do in a particular situation. The second thing is that this is an example of where we're using this idea of a runtime variable here. So I don't know the drink. The planner doesn't know the drink they've requested at this point. All they know is they've requested a drink, and we're going to serve them the drink they've requested, whatever that is. But we've reasoned about it at the knowledge level. So just to show you in practice what this looks like, here's an execution of the single drink order. Okay, so nothing very complicated there, but you saw the execution of that simple plan. We can also look at more complicated plans. So in this case, I have an example of a multi-agent interaction plan. So the idea that two people come into the bar now and are asking the agent to drink. So this is similar to the scenario that I had at the start. So using these actions, we can generate a plan, tell one of the agents to wait, greet the other person, ask them for the drink, acknowledge the drink, serve them the drink they requested, say goodbye, thank the other person for waiting, ask them for a drink, acknowledge, serve, goodbye. So again, nothing very complicated here, but it falls out of the kind of reasoning that we had with these knowledge level actions. One of the nice things about planning is that if we make little changes to the nature of the actions, we can change the nature of the interaction we have. So here's another type of multi-agent interaction that we might end up with in this scenario. So say two people come in and they order as a group. So in this case, the robot might greet the first person, ask the first person for the drink, ask the second person for their drink, acknowledge the orders, and then serve both of the people. Both of these are valid in interaction plans, and they've both kind of fallen out of the same kind of reasoning we've performed. So just to give you another example, here's the robot with two people now in the bar.
Aaron, just to mention that we don't hear the audio of these videos, so I don't
you don't?
If you want,
okay,
if you want
sorry.
to comment what
oh, sorry. I guess, okay. No, just give me a second then. Let me reshare this. I forgot to click on. Okay, thank you. Okay. Sorry about that, everyone. Can you see the slides? Oh, what the heck happened? You hear any sound now?
Yes.
Okay.
Hello.
Hi.
I'll be with you in a minute. What do you want?
I would like a water, please.
There you go.
Thank you.
Goodbye. You're welcome. Thanks for waiting. What do you want?
Give me a Coke, please.
Here's your drink.
And then the then the interaction continues with that. So what we see in that video there is really the execution of this plan here, where one of the agents is being told the customer is being told to wait. We go through the transaction with one, and then we continue with the transaction with the other person. So the final thing I want to mention is, because the planner is a contingent planner, we can also generate some interesting interaction plans that look like this. So we can greet an agent, ask them for a drink, and then we can build contingent plan branches, potentially for reasoning about the different kinds of drinks that someone might order. So for instance, if they ordered a juice, we can consider that. If they ordered a water, we could do something different. If they ordered a cola. And in each of these branches, we might have very different subplans. So if it's the case with juice, we could ask, would you like that in a glass? If it's water, we could ask, would you like ice with that? And so on. So being able to combine the idea of contingent planning with this knowledge level planning gives you another tool to be able to generate these plans to deal with some of the uncertainty in the environment that comes up when you're interacting with humans. Okay, so at this point, we're going to switch over to Luca. I'm going to stop sharing. And I apologize for the video mix-up. Luca, I'll let you.
Okay. There is a question. Maybe we can see if
Sure.
some well, yes,
okay.
in the chat.
Can the sensing action have a weaker effect of just increasing my belief that I know what the state is? So in the case that I've given you with PKS, it's a very definite sensing effect. So you either come to know one of the values. So it's definitely the case yes, or it's definitely the case no. With some of these modal logic representations, there are representations that will give you degrees of belief. So in fact, you can in fact model that as an increasing my belief. You can rule out certain possibilities, which increases your belief that it's one of the remaining choices. We can actually kind of sort of do that with PKS, but you have to jump through some representational hoops. There's another question. How are the actions that can fail accommodated?
I think I will answer to the second.
Yeah, Luca's going to talk about execution in his part, and then I can say a few things about that then. I was wondering, are there any works considering deception in the agent's knowledge system? That's a great question. We aren't. I'm very interested in that. There is some recent work by Thomas Bolander, who has been looking at false belief tasks with DEL planning. And he's actually implemented a system using DEL planning on the Pepper robot that is in fact able to deal with different types of deception. It is actually something we're looking at in our own work to allow for more knowledge or sort of more beliefs rather than hardcore knowledge. But yes, there are other people that are working on that problem. Okay. Are there any other questions? Otherwise, I'll hand off to Luca.
Okay. So what I'd like to do is to continue this part by illustrating another approach for planning at the level of knowledge. And then I will focus most of this second part on execution, because we have seen at the beginning that there are many issues in planning and plan execution in HRI, and for sure epistemic planning is important but does not solve all the issues. So let me start from this approach that is based on a description logics. And so description logics is a family of logics that are based on three main concepts that are concepts, individuals, and roles. And it's quite easy to map these elements in something that is useful for planning, because we can map individuals in description logic as states, concepts as properties of the environment that must be true on states, and roles as actions. So with this mapping between the entities of a description logic and the elements that we need for planning, it is quite easy to use description logics for modeling planning domains. And I will very quickly show this example of a particular logic ALCKNF, where all these letters stands for some elements of the description logic that is used. And this is, in my opinion, quite a nice way of modeling a planning domain with knowledge. So we can express in this logic preconditions, like what you see here. And so this is a way of describing formulas in this logic. And the intuitive meaning is that if here we have an epistemic operator, K, that is the same that has been mentioned in the previous part. And so this formula expresses the fact that for every state in which C is known to be true, there exists a role, so a link between this state and some other state. So this is used to model preconditions. So in other words, this is a formula that expresses that C is precondition for the action R. And we can express effects like this one, in which we say that for each state in which C is true, then all the states that are linked to the state through the action R must be such that D is true. And so this is the effect of an ordinary action, in which you say that if C is true in the state before the execution of the action, then D must be true in all the states after the execution of the action. And we can express sensing actions in a similar way as Aaron explaining that, for example, this formula here says that for every state in which C is true before the execution of a sensing action, you can come to a situation in which either all the successor states with respect to the action RS are such that D is true, or all the successor states with respect to RS are such that not D is true. So what is interesting here is that this junction makes the system able to reason about these two possibilities. And at planning time, we don't know what would be the actual effect of executing this action. So the reasoning system and the planner, as was mentioned also by Ron, can continue its reasoning by just considering these two cases. One in which all the states that are connected with this action are such that this is true, and another option, another possible world in which all these states are in all these states, D is false. And this means that the planner can reason on all these cases, can generate a conditional plan. And then only at execution time, when the action RS is actually executed in the real environment, then we know that only one of these options will become true. So I think this is important to understand that at planning time, we will not know what will be the outcome of the action, but this will be known only at execution time. What is also nice of this logic is that we can, in a very, I would say, elegant way, describe inertial properties or frame axioms. And so we can say that if C is true in a state, either we will be able to prove not C, or C must be true also in the successor state. So in other words, we can introduce an additional epistemic operator that is a default assumption operator. And this formula here says that if it's consistent to assume that C is true after the execution of the action, then C remains true in the successor state. Otherwise, for example, if there is some effect of the action R that makes not consistent to assume C anymore, then this part will not apply, and so C will not be valid. So in this way, we can model frame axioms, and we don't need in this language, for example, the delete operator that you have in strips, in which you have explicitly delete the some conditions that becomes false after the execution of an action. So this makes the system very simple, because we can just model our domain in terms of preconditions, effects for ordinary actions, effects for sensing actions, and frame axioms. And also it's interesting to notice that if we don't put in the knowledge base one frame axiom like this, then we can implement the notion of forgetting. So if this axiom is not in the knowledge base, then it means that we want to model the fact that after the execution of an action, the value of C becomes unknown. So the notion of forgetting something. So how can we do planning with this language? That's quite easy. So we just create a knowledge base describing the planning domain with a set of logical formulas as the ones that I described before, of course, for all the fluents and actions that we want to consider. Then we have the representation of an individual in the description logic that represents the initial state. And this individual will not be complete, so we don't need to specify all the values of the properties of the initial state. So this can be an incomplete description of the initial state. And then we have a concept describing the goal. And plan generation, for plan generation, we don't need to write a specific planning algorithm, but we just can use the reasoning tools of the description logics. And so we can just prove that this concept contains some instances. So this is an instance checking, a classical instance checking problem in description logics. And so what is the meaning of this is that from the planning domain, we can derive that the individual representing the initial state belongs to a concept that describes the goal. So this concept contains all the information that, so if you can prove that init belongs to this concept, then this concept contains the information for the plan. So the construction of this concept is such that from this concept you can get the plan. Because in this concept there are all the roles that correspond to the actions that bring the system from the initial state to a state in which the goal is achieved. So what is also interesting that so reasoning in this description logic again doesn't need a specific algorithm, you just use instance checking, and it is plan existent, is p-space complete. So even if the system looks very complex, we actually are in complexity domain, which is similar to other planning problems. Of course, the generation of a plan requires a constructive proof of this entailment, and this means that, of course, in the worst case, you may need exponential time and exponential space. So this system has been implemented like both by using description logic engines, but also we have a simple implementation in C++. So if you're interested to play with it, you can just ask me. But I have to say that using other conditional planners is equivalent, because at the end, all these frameworks are kind of just different variations of the same problem. Now, let me move to actual execution. So how can we use these systems in order to produce plans for HRI, and in particular then for executing them? Well, in general, what we want to do is to create a knowledge base that contains robots' knowledge about user needs. For example, a service robot with the goal of serving users, like the example that we have seen in the previous part, would need to represent the fact that the user has some needs. For example, the user is thirsty, hungry, and so on. And we need to gather information during the interaction with actions like ask and answers. And in general, we need to generate conditional plans because it is not reasonable to assume that the initial knowledge of the robot is complete before executing the plan. So this is an example in which we have combined some components. So a conditional planner, ROS plan as execution, and PetriNet plans for the monitoring that I will show in the next slides. Just to mention that with this framework, we can generate a plan, and we can execute this plan in the real world. And here you can see, I will just go quickly through this. Sorry, I removed the audio because probably it's not very interesting. So this is a very simple plan in which the robot is asking questions, and depending on what is the answer of the user, it generates some other actions. So here you have different flavors of this task. And what is interesting here is to understand that the plan itself is not very complex. So usually when you plan for human-robot interaction, you don't have complex plans. Plans are short, and the complexity of planning in HRI is not in the combinatorial explosion of the state space, but it's in the flexibility to generate different plans according to the situation. So I will probably come back to this later on, but I want just to mention that even if this plan looks very simple, and so you can think, why should I use a planner? I can write this plan manually myself. I will show you, first of all, that this is not the case when we consider also plan execution, and also that in many practical applications, it is true that this plan is simple, but it's always the case that you have to generate many of these plans. And so writing all these plans manually will not be very effective. Okay, so what's the problem? The problem is that when you execute these plans in the real world with the users that are not familiar with the robot, so when one of the key elements of robot in public spaces is that users that interact with the robot are not familiar with robots. So it's very different from, for example, the use of a robot in a factory in which the interaction can be done, for example, with workers that are trained and they know how to use the robot, they know what the robot can do. When you put a robot in a public space, you don't have any of this information. And so users, they don't know what to do. They start touching the robot or doing something that is very difficult to predict. So there is a lot of uncertainty when designing a system for HRI. First of all, of course, it is not possible to model all the intentions of the users. There are noise in communication and perception. In a public environment, typically there is a lot of noise for the perception system, for example, for speech recognition. And in general, it is difficult to have an accurate prediction of future states. So, as already mentioned, a system, an HRI system that assumes perfect abilities of the robot, let's say a system that is making too strong assumptions, will not be effective in the real environment. And so what we want to do is to study how to deal with unexpected situations. So we cannot avoid in HRI tasks to have situations that are not predicted, modeled, or described in the plan. So there will always be some situation in which the system will be in a state that was not predicted explicitly in the plan. And here we will consider two cases, one in which this unexpected situation can be described with variables that are in the planning domain. So this means, for example, this is a case, for example, in which an effect of an action has not been modeled or considered. So during the execution of the action, something happened that was not predicted. So in this case, when unexpected situations can be described with variables that are in the domain, then we can detect these situations with, for example, some monitoring of the plan and solve these situations with replanning. And this is an example of monitoring and replanning, and I would like maybe Ron to comment it because it's related to the James project.
Thanks, Luca. Yeah, so in terms of replanning here, we have two very common situations that we see in HRI. So the first one is an example of simply you have low confidence in the speech recognition. Somebody says something and the sensors of your system don't pick it up. So in this case, you could imagine in the bartender scenario, the robot asks a customer for a drink, and what you get back is mumble, mumble, mumble. So the customer was not understood. So this is a case where replanning, if you're monitoring the expected state that should result from executing your action, the replanning mechanism can kick in here and simply detect the fact that the information you thought you'd get, in this case, the customer's drink order, wasn't available. So replanning would generate another plan. So in this case, you might say generate some sort of response to the customer. I'm sorry, I didn't understand you. What would you like to drink? These are examples of this idea Luca was talking about of detecting from within the model. So we have a model of the kinds of expectations, the kinds of outputs that should come from these actions. The second situation is an interesting case in HRI of often you ask for information and you get more back, but sometimes people say things that you didn't expect. So in this case here, you can imagine greeting a customer, someone comes in, you say hello. And then rather than asking them for the drink, they tell you, I would like a beer, I would like a cola. They just give you the information. At this point, it doesn't make sense to ask them for the drink because you actually have the information that that action would have provided. So this is a different type of monitoring and replanning here, where in fact you can generate a new plan to just respond to the fact that you have this information. So in fact, you could proceed with the action of simply serving the drink. I guess the important point with both of these, and this goes back to what Luca was saying about, often these plans are really short, but when you're interacting with humans, you often have to do a lot of replanning. There's a lot of uncertainty, and the responses you get from humans are often unpredictable. So I'll pass it back to you, Luca.
Okay, thanks. But now I want to focus on this other situation, that is when something happens and this something is not modeled in the domain. So what you can do in this case? Well, of course, you can maybe update the planning domain. So you realize, for example, that a state variable is important for your for the execution, and you add this state variable in the domain, you modify the actions, preconditions, or whatever, you generate a new planning problem, you generate a new plan, and you go on. Notice that usually here, you can do this automatically, so usually this part must be manually, so it means that there must be a knowledge engineer who would understand how to encode the situation in the system. But what is the problem? It is that even if you do this, when you execute the new plan, there must always be the case that there will be another condition that makes the plan fail, and that there will be maybe other unmodeled variables that you have to add. So this process, as you can imagine, is not easy, and also brings performance issues, because you know that the planning problem, solving a planning problem, is usually complex. Let's say that it's practically exponential. So it means that whenever you add a state variable in the system, you are significantly increase the difficulty and the planning problem. And very often you really don't need to reason about this variable, because maybe what happened is very specific of that situation that can be solved in another way. Let me make this example. We have a robot that has to reach a target. So this is our robot, this is the target, and the goal for the robot, the plan of the robot is to move from this initial position to the target. And we have an unexpected situation that is a person in the corridor. Okay, so let's assume the case in which the planning domain does not model the presence of people. So how can you solve this situation to get to the goal? Well, we can consider a solution at the action level. So the go-to action, so the action that is under execution, is good enough to avoid the person, and so to solve the situation without changing the plan, by just, for example, executing an obstacle avoidance. Or you may consider a solution at the reasoning or planning level, in which the system monitors that, for example, this action is not feasible because this obstacle doesn't prevents the robot to reach the goal, and so you come up with a different plan to reach the goal. Now, what we are interested in here is to exploit the person, and instead of considering the person as just an obstacle, we can even take an opportunity for interaction, or we can anyway solve the problem with some form of interaction. For example, the robot could talk with the person and explain that he needs to reach the goal, and can, for example, ask the person to give the way free. So how can we do this? So how can we integrate this solution? Well, of course, there is one possibility is that we can change the action. So we can add some code at the action level to implement this behavior. So, I don't know, an if statement in the C++ code of the action that says that if there is a person in front of the robot should say something. Or, of course, we can model explicitly people in the planning domain, and so having this as a plan that is generated with planning. What I would like to discuss in this final part of this lecture is a third way. So a way of obtaining this behavior here, that is the one that we are interested in, without modifying the low-level actions and without modifying the reasoner, the planning domain. Why this? Because I think that there are so many of these situations that would be really impractical to consider all these situations at the action level. So to encode all these solutions in the implementation of the atomic action, and at the same time, it will be impractical to expand the planning domain to consider all this situation. But still, we want to do it in a declarative way, because we want to make sure that what we do has a semantic, okay? So the question is, how can we implement this kind of behavior in a declarative way? And in other words, what we can we can see the same aspects from a different perspective. When we have a system based on robot planning that has to interact with users, and in particular with naive users, so users that do not know what the robot is doing. Then, as already mentioned, we have this issue that the plan that is generated by the planner is usually not suitable for execution. What we miss is what we call robustness. So we should add something here to make this plan more robust with respect to the interaction with naive users. So what we have proposed there is this system, planning and execution component that has the idea of having a nominal plan generated by a planner from domain and goal, and here you can have whatever you want, but then add another phase of generation that is what we call robustification. So this is a process that, given a nominal plan, so you can think about this nominal plan as the optimistic plan, so the plan that will reach the goal if everything goes well. But since we know that this is not the case, especially in HRI, we want to add some other declarative rules. We call them execution rules, and have this process that, given the nominal plan and the execution rules, generate another plan that is more robust. What does it mean? It means that here there is a higher probability that this plan will reach the goal, even when there are interactions with the users that are not modeled here in the domain. And what is interesting is that the variables that we use for the execution rules must not be necessarily the same of the variables that we use for the planning domain. So it means that here we can introduce additional knowledge without affecting the domain, the planning domain. And then, of course, when we execute this plan on the real robot, we have more situations in which the plan will get to the goal. So what are execution rules? They are just declarative rules that you can consider as kind of patches that you want to attach to the nominal plan in order to consider some situations that are not modeled. And they usually have this form. There are other forms, but let's focus only on this form. Let's say very simply that if something happens during the execution of an action, then you can specify some recovery procedure. So in this way, when we apply these rules to the plan, we will increase the situations in which the plan can do something good. And also, of course, all these execution rules are evaluated only at execution time, so they do not affect the planning process, and they will change the nominal flow of the actions that are in the plan by introducing something that can be considered as recovery paths or recovery plans, in which when something happens during this execution, you do this, and this is something that usually you create some actions or some structure that would solve the situation and possibly go back to the nominal plan in the next steps. So this has been implemented in this tool, Petrick plans, that is available also as a Docker container in the AI4AU platform. So this probably, hopefully in the next months, there will be in AI4AU the possibility of combining different tools for AI, in particular also for planning and for human-robot interaction. So, of course, I invite you to give a look at it. I don't want to go too much into the details. I will show some examples later on. Just mention that Petrick is a very powerful representation language, which we can represent all the structures that are important for plan execution in robotics, and there are procedures to generate PNP from the output of several planners, integration with ROS plan, with ROS, and so on. Okay, let me show you some examples. How do we implement these execution rules in PNP is to exploit the interrupt operator that is available in PNP. And this is an operator that just allows to say and to model with the Petri nets the fact that while the robot is executing an action, so while the state of the executor is such that one action is executed, we can check for some condition, and if the condition becomes true and this transition is enabled, then we can suspend, let's say, the normal execution of the plan and start to do something that is a recovery procedure. So we can imagine here you have your nominal plan, and here you attach to this nominal plan a set of structures like this that monitor if the plan is going well, and if there is something happening during the execution, you move to do something else. And all this structure is automatically generated by a declarative specification of rules. Here you see some examples in which you can specify what to do if something happens during the execution of some action. And what is important, again, I repeat that the state variables, so the variables that you see here in these rules, must not be necessarily the same of the variables that you use in the planning domain. So for example, if you want the robot to do something when the battery is low, but you don't want to reason about this feature at the planning domain, because it is something that maybe is not really relevant for your task, then you can consider low battery as a property, as a variable that is used only at execution time, and you don't need to use this variable at planning time. But in any case, with these execution rules, we are not changing, as I mentioned before, neither the implementation of the action. So here the go-to action remains the same, and we are not changing the planning domain. So what we can do is that when we implement this step here, so given the nominal plan and the execution rules, we can generate a very complex PNP. And this is an example of a PNP that has been generated during one of our projects, and I will show you in a while a video of the execution of this PNP. So this is a PNP with around 100 of places and transitions. For the Coaches projects, we generated plans with thousands of places and transitions. So let me anticipate one question that you may have. Can we do the same with state machines? So the answer is, in theory, yes, because for any Petri nets, there exists an equivalent state machine. The problem is that in the worst case, the size of the state machine is exponential with respect to the size of the Petri net. So this means that using this formalism, you have guaranteed that you can represent a very complex behavior with in a compact representation, so in a exponentially more compact representation with respect to state machines. And also, if you again ask, can I do it manually? Can I write this behavior manually? Well, you can imagine from this picture that it's very complex. And why we need planning? Because again, this has been generated after the plan. If you change one condition at the planning domain, then you need to generate a new plan, and when you apply the execution rules, you will generate another PNP. And again, do this manually will be too difficult and practical. Okay, to conclude this part, let me show this video in which you can see the difference between the execution of the plan without and with the execution rules. So here the task of the robot is very simple. The robot just has seen that there is a person in front of the printer. You don't see the printer that is behind this plant, and the robot goes to the position to ask the person if she needs some help. Now the plan is just go to the printer and then ask the person. But you see that, for example, without the execution rules, these two actions that are in sequence, one is go to the printer and the other one is ask. The second one, ask, will not start until the first one is completed. And so you see that there are situations in which, for example, here the person is approaching the robot because she wants to interact with the robot, but the robot is still executing the go-to action, so it's trying to avoid the person to reach the final goal. Of course, this is a behavior that is not nice, because the user would like to interact with the robot while the robot is still executing a go-to action. Here with the execution rules, we can say, for example, that if the person, if you encounter the person before, during the go-to action, you should interrupt the go-to action and proceed with the interaction. And so now on the execution with execution rules, by just adding this rule, you can see that the behavior of the robot will be that as soon as the person is detected, the go-to action is interrupted and the person can start the interaction. And here we'll see another example of situation in which the robot goes to the printer, but the person goes away meanwhile. And now if we have the nominal plan, we just start asking a question to the person, but there is nobody anymore. So again, here you can add execution rules that say that if there is no people at this point before executing an interaction, you can interrupt this task and restart the plan. Okay, what is also interesting that you can do this in an incremental way. So you can execute your plan, look, see what happens, understand what are the conditions in which the plan is not satisfactory, and you can add these execution rules in an incremental way. Okay, so let me conclude, and then of course we'll come to the questions. Why we believe that HRI and planning can have an important role, and there are many opportunities. Because you know that the perspective of AI is changing in the last years. So previously, we were focusing on AI defeating humans. So we are focusing on having AI systems that were competing against humans. So AI winning on chess, on Go, on poker. And so we were implementing systems with the goal of proving that AI can be better of humans. But now there is a trend, a new perspective of what is called a human-centered AI. And you know, for example, the European Commission is pushing a lot this concept, in which we switch from the concept of AI as a superhuman, and we move to the concept that the AI must be designed in order to help humans. So in this context, the human AI interaction would be a fundamental topic. And of course, we believe that planning technology applied to HRI and in general to human AI interaction is very important, because it enables the flexibility that is required to address all these complex problems, and allows to give a principled solution to many tasks that are very complex. On the other side, we have seen just some few examples of how these problems can be tackled with these techniques, but for sure we need more both theoretical and practical results, and there is of course a wide applicability to real-world systems. Okay, we'd like to acknowledge some projects in which this work has been carried out, and I think also interesting to mention that there are also ongoing projects, and possibly future projects. So the use of planning techniques in tasks involving humans will be, in our opinion, more and more interesting. Okay, thank you. I don't know if Ron wants to add something on the conclusions.
No, that sounded great to me.
Okay, so
thank you for this very nice and comprehensive talk with a lot of illustrations. Any questions, remarks from the audience?
Okay, I can read some questions in the chat. If I have 1 minute,
Please do.
I would answer. So one question is, are execution rules predefined by robot designers or can be generated by planner or some other verification techniques? So very good question. At this moment, at least in the papers that we published, we consider that these are predefined. What we are doing is to understand if it's possible to learn these execution rules. Because when you run your plan in the environment, you can collect data, especially data about failures. And so you can create a kind of database of what happens. So you can create databases or data sets in which you notice that in this situation, during the execution of the action, something happens and the robot was not behaving as expected. So I think that one option could be to apply learning techniques to learn these execution rules. Anyway, for the moment, yes, in the papers that we mentioned, they have been designed by robot designers.
On this same topic, are you familiar with some of the approaches that extend a temporal planner from general principles with specific execution rules? I was thinking about the work that was performed in Sweden around time planner by Petrick and his co-workers. How do you compare? Because Petrinets gives you some synchronization facilities and so on, but they do it differently with.
Yes. Well, I think that what I would like to stress here is something that comes after planning. So of course you can have any planner that takes into account whatever you want. So now what in the second part I've been discussing what you can do after planning. So whatever is the planner, I still think that by definition, the problem domain must be an abstraction of the world. And it's probably impossible, especially in HRI tasks, to have all the information modeled at the planning domain. Yeah. So what I think is that in any case, whatever is the planner that you're using, there must be still situations that maybe you don't want to model at the planning level. For example, the fact that the battery is low and any other issue. So what I think is that we need another piece of architecture that is what you do after planning in order to create, to manipulate this plan and generate another one that is more robust.
Yeah, if I remember correctly, they were doing it also after planning.
Okay.
But in your case, are you doing it reactively or taking into account just the specific context in which you start planning?
So the definition of the execution rules is done.
Is general.
It's general, yeah. And then the actual execution is reactive, yes, because we add the interrupts, and these interrupts at the monitor, the PNP engine will monitor the fact that some condition happens during the execution, and if this happens, it will move the plan in another direction.
Yes, but this is already in the synthesized Petrinet.
Yes.
Yeah. Okay.
If I can just add to that, because you mentioned temporal planning, yeah. I have a PhD student that's currently working on adapting his temporal planning system to use the kind of execution framework that Luca's group is using to bring these together. And in fact, we are also adding some of these ideas of epistemic planning to temporal planning with this model of execution. So adding some additional tools to the toolkit for everyone.
Excellent. If there are any references on this, please point them.
I will put some references into the Slack channel, and for the people that asked some questions earlier as well, I have a few other things I can add to that in Slack.
Excellent. Many thanks.